Any good solubility chart, like this one, will pretty easily tell you that potassium and chromate put together form a soluble ionic compound. And this is a bottle of solid potassium chromate that's been here in this laboratory since, I think, before time began. A table like this will also pretty easily show you that lead combined with chloride makes an insoluble, in this case white insoluble product. This is a bottle that I prepared on September 3rd of 2004 by taking some distilled water and putting some lead chloride in it. And that white stuff has just been sitting there since 2004 because lead chloride is insoluble. And here I'll take some of the supernatant liquid that sits above the lead chloride in that bottle and put that into another beaker. And here's what it looks like when I take some of that dissolved potassium chromate and add it to another beaker of distilled water. Basically, I'm just making a more dilute solution of potassium chromate. And since my solubility table says that lead chloride is insoluble, that supernatant liquid should just be pure water, right? So why, when I add potassium chromate to it, am I getting this yellow precipitate? And it just kind of keeps coming, and I'm getting you, and like, what is that? I'm sorry to say, guys, but you may have been fed an overly simplified version of reality. Things that are technically insoluble, according to a simpler chart like that, are actually very, very slightly soluble, some more slightly soluble than others, but it's measurable, and we are trying to account for that right now. Here's a little diagram that shows the dissolving of the lead chloride. Most of the lead chloride stays as a solid at the bottom of the container, but at any given time, those little water molecules are coming in, colliding with the surface, dislodging some of those ions, and getting them up to go around in the solution until they find each other and settle back in as a precipitate. The rate of this happening is equal to the rate of this happening after a short time, and so we have a solubility equilibrium. I'm sorry, I know it hurts to find out that you've been lied to, but I really wanted you to hear it from me instead of out on the streets. A chart like this is super useful for some general predictions about whether something is soluble or insoluble. But when it comes down to it, all these things over here that are listed as insoluble are actually slightly soluble, and they have known equilibrium constants. We call them Solubility Product Constants, KSP. And finally, a chart like this will pretty easily tell you that lead and chromate, when they get together, will form an insoluble compound, in this case a yellow one. What's not as obvious from this chart is that there's actually varying degrees of solubility between these things. This one is actually less soluble than that one. So we usually start by being told that things are either soluble or insoluble, and that's it. But the new reality is that there's actually a big sliding scale of solubility. Some things are really soluble, some things are only slightly soluble, and some things are really, really soluble only on a tiny scale. But even those are actually dissolving and undissolving a little bit. Now let's solve a couple of problems using KSP, or the Solubility Product Equilibrium Constant. The solubility product is what we call it. It's the equilibrium constant that describes the dissolving of an insoluble salt. Now we're learning that they're not all completely insoluble. Most of the salt remains solid, but a small amount of ions dissolve and then undissolve at the same rate, thus setting up an equilibrium. And so we'll have to write the dissociation equation. And when you do that, you would include any charges that those things have. This is just a general one. And you can write an equilibrium expression for this because it's an equilibrium. So you'd normally write K equals the two products, one of them squared, over the reactant. But in this case, the reactant is a solid, so it's a heterogeneous equilibrium, and you're not going to include that solid. So you just end up with something that looks more like this. Okay, and you'll see some examples of that. Now, what if I'm interested in how much lead is actually dissolved in this liquid there? I'm seeing evidence that there is lead in there, but how much? We can calculate that if we know its KSP value. So we're going to set up a problem. Here's a equation for the dissolving of the lead chloride. 1 lead and 2 chlorines for each one. What is the concentration of lead in a saturated solution? Okay, what you're going to see next is very similar to other equilibrium problems you likely have done if you're watching this video. And so what I'm going to do is I'm just going to rewrite the dissociation equation, just so I have it down here. And the 2Cl's over here, those are both aqueous. I'll omit that for now. Then I'm actually going to do an ice table like I've done for other things. Okay? And when you're doing ice tables for solubility equilibria, you often say, all right, well, I need my initial amounts. And at the start, before anything dissolves, I'm going to have 0 and 0 of that. But how much solid is actually in here? Well, you know what's cool? It really doesn't actually matter. Because it's a solid, its concentration is constant. So we can just put a question mark or smiley face or whatever you want to put there. We don't know it and we don't care because it's a solid. I do know, however, that after a while, some of that is going to go down and dissolve into the solution, and we'll call that X. And we're going to call that X, and it's the molar solubility. We have a special name for that X. It's called the molar solubility. I will label that. All right, let's just write that over here. With X equals molar solubility. Okay. All right, so keep that in mind because you'll see that term in different questions. X is the molar solubility. So we're going to end up with a final concentration of question mark minus X. Don't know, don't care, and let's move on. I am concerned about these two, though. So this is going to end up as X. That's going to end up as 2X. My solubility product expression is going to be lead and then chloride squared because of that 2 there. And I'm actually just going to take my X value, 1.6 times 10 to the minus 5th, and I'm going to plug X in for that, and then 2X squared for that, which is going to simplify into 4X cubed. And when I solve for X, I get 0.0159 moles per liter. And that right there, because X, and we got to remember to answer the question. So the PB concentration is equal to X, which is 0.0159 moles per liter, and that is my answer. Okay. The chlorine would be 2X, which would end up being 2X equals 0.0318, and that's going to be equal to the chloride concentration if you were ever asked about that. Okay, so you use the KSP as your equilibrium constant and solve it, remembering to omit the solids in the equilibrium. Okay, now it's your turn to try. Here's one for the dissolving of silver carbonate. And the KSP for silver carbonate is 8.1 times 10 to the minus 12th. So it's a little bit lower than the lead chloride one. Calculate the concentrations of silver and carbonate ions in a saturated solution. So if you like, take a moment, pause the video, try this one out, and come back in a couple seconds for the answer. All right, when I did this, I got silver and carbonate concentrations of 2.54 times 10 to the minus 4th, because X came out to be 1.27 times 10 to the minus 4th. You can see my ice table, my expression. It's 2X squared times X, which again is 4X cubed if you simplify it. And then the carbonate is equal to X, which is 1.27 times 10 to the minus 4th. So if you got that, congratulations. We're off to a great start. Okay, so now I want to do a couple in reverse. You'll see problems like this where it'll tell you, hey, the molar solubility of lead 2 iodide is 0.00130 moles per liter. Okay, great. Let's calculate the KSP for this one. All right, so I'm going to start by setting it up the same way as the other one. I'm just going to rewrite this so it's down below. Okay, and I'll make my ice table. Again, don't know what that is, don't care either. So question mark, so it's going to go down by X, up by X, and up by 2X. And again, question mark minus X. You can mess around over there if you want. The KSP expression is equal to the concentration of lead and the concentration of iodine squared. Okay, and now this one is the opposite type problem because we know the molar solubility, which is X, and we're trying to find KSP. So let's go in reverse. So the lead concentration is going to be X. The iodine concentration is going to be 2x, and then we're going to square that to get our final answer. So let me plug these in. The point. So right here, that equals x. So make a note of that. 0.00130 and 2 times 0.00130, and then we're going to square that. And a few taps of the calculator later, I find out that my KSP value for lead iodide is 9 times 10 to the minus ninth. And because it is an equilibrium constant, we've all agreed to not put units on it, so you can just be happy just putting the unit. The concentrations, you make sure to put moles per liter at the end of it, because concentration should have a unit, but the equilibrium constants should not. All right, I have one more pause the video moment for us today. This is the dissolving of silver phosphate. And in this one, it's very similar. I've given you the molar solubility, which is your X value. Calculate the KSP for silver phosphate in the same manner as before. And if you did that, that makes me happy. And here's my solution for that. It turns out the KSP value is 1.81 times 10 to the minus 18th. And this one ended up working out to be 3x cubed, because there's 3 silvers for every phosphate, times x, which worked out to be 27x to the 4th. That's getting crazy. And 27 times our x value, molar solubility, to the 4th, they get 1.81 times 10 to the minus 18. So excellent job on that one. I want to end with a slide. I've already worked out the solutions here for 2 other ones. Okay, copper sulfide and bismuth sulfide. I like to do these ones in class for a couple of reasons. Number one, the KSP for this one is going to be equal to x squared. The molar solubility is 9.2 times 10 to the minus 23rd. Now think about that. That's like literally 1 unit of copper sulfide out of an entire mole of molecules, 6.02 times 10 to the 23rd, that dissolves in a water-based solution. And that's pretty crazy that people are able to find out how to do that, how to measure that. But it is measurable, and we have that information. Now, if I square that, I get 8.5 times 10 to the minus 45, which is getting a little scary. Very tiny exponents there. But look at bismuth sulfide. Its molar solubility is 1.0 times 10 to the minus 15th moles per liter. But its KSP is 10 to the negative 73, which is ridiculous, right? And I did this not only to show the ridiculousness of some of these numbers, but also the fact that unless they have the same number of ions, like the same expression, x squared or 105, 108 x to the 5th, you can't really compare solubilities based on their KSP values, because those are equilibrium constants. Copper sulfide actually has less solubility than the bismuth sulfide, but the bismuth sulfide has a way tinier equilibrium constant, because this amount, which is very tiny, gets taken and squared and then cubed again, and it just gets ridiculous after that. So don't make that assumption based on KSPs. It's better to use molar solubilities to compare the actual solubility of a certain type of, or certain set of compounds. All right, well, there you have it. I hope you enjoyed this episode on solubility product, getting us going on solubility equilibria. If you have questions, you can send them to me in the comments or directly. In the meantime, happy solving and have a great day.